Imagine standing in a dark field on a clear night. Above you, the stars stretch across the sky. Some are dozens of light years away. Others are hundreds, thousands, millions. The light entering your eyes began its journey long before this moment. Some of it left distant stars before modern civilization existed. Some of it began traveling before the first human cities were built. Some of it started moving through space before recorded history itself. And yet, despite these unimaginable distances and timescales, there is something strange about every beam of light that reaches you. Something so strange that even Einstein struggled to fully understand its implications. Because according to our best understanding of physics, light may not experience its journey the way we imagine. In fact, from the perspective of light itself, the trip from a distant star to your eye may not take years, or centuries, or millions of years. It may not take any time at all. Tonight, we are going to explore one of the deepest questions in physics, a question that sounds simple enough to ask. What does light see? At first, the answer seems obvious. Light sees the universe. Light travels through space. Light encounters stars and planets and galaxies. Surely light must experience something as it moves. Surely a photon traveling across the universe witnesses the cosmic landscape passing by. Yet the deeper physicists explored the nature of light, the stranger the answer became. Because the universe appears to treat light differently from everything else. A rock experiences time. A planet experiences time. A human experiences time. Even an atom experiences time. Light does not. Or at least, that is what modern physics seems to imply. To understand why, we must begin with a simple thought experiment. Imagine you could run alongside a beam of light. Faster and faster you go. 100 kilometers per hour. 1,000. 1,000,000. Eventually approaching the speed of light itself. What would you see? The question sounds innocent, but it would eventually change the history of science. In the late 19th century, physicists believed they understood motion reasonably well. If you throw a ball while standing still, the ball moves at a certain speed. If you throw the same ball while riding on a train, the speeds combine. Motion adds together. Everything seems straightforward. So scientists naturally assumed light should behave the same way. If you move toward a beam of light, perhaps it should appear slower. If you move away, perhaps it should appear faster. The logic seemed undeniable, and yet experiment after experiment revealed something impossible. The speed of light never changed, no matter how fast the observer moved, no matter which direction they traveled, no matter how the experiment was performed. The result remained stubbornly the same. Every observer measured exactly the same speed. Light appeared to ignore the ordinary rules of motion. For years, this result puzzled physicists. The measurements were correct. The mathematics was correct. And yet the conclusions seemed absurd. How could every observer measure the same speed? How could motion fail to affect light? Then, in 1905, a young patent clerk named Albert Einstein looked at the problem from a completely different angle. Instead of assuming the measurements were wrong, he assumed they were right. And from that assumption, he reached a conclusion that would transform our understanding of reality. Perhaps space and time themselves were changing. Not light, space and time. The idea sounds impossible at first. After all, space seems fixed. Time seems fixed. Minutes pass. Distances remain distances. The world feels stable. Yet Einstein realized something remarkable. If the speed of light is truly constant for every observer, then space and time cannot be absolute. They must adapt. They must stretch, contract, flow differently depending on motion. And suddenly, a completely new universe emerged. A universe where time itself could slow down. A universe where distances could shrink. A universe where the experience of reality depended upon how you moved through it. This became the theory of special relativity, one of the most successful scientific theories ever created. Its predictions have been confirmed countless times. GPS satellites rely upon it. Particle accelerators rely upon it. Modern physics relies upon it. Again and again, the universe behaves exactly as Einstein predicted. And hidden within special relativity lies a profound implication. The closer something moves to the speed of light, the more unusual its experience of reality becomes. Time slows down, distances contract. The universe itself begins changing, not as an illusion, not as a trick, as a measurable physical effect. Astronauts experience it. Particles experience it. Everything moving through space experiences it to some degree. Usually the effect is tiny, far too small to notice in daily life. But as speeds increase, the effect becomes larger and larger and larger, until eventually we arrive at light itself. And this is where the real mystery begins. Because according to Einstein's equations, something extraordinary happens at the speed of light. Time stops, not slows dramatically, stops. The mathematics points toward a reality where a photon experiences no passage of time between its creation and its destruction. No aging, no waiting, no journey. This is one of the most astonishing conclusions in all of physics. A beam of light may spend billions of years crossing the universe from our perspective. Yet from the photon's perspective, those billions of years simply do not exist. The journey contains no duration, no passage, no experience of time. If this is true, then what exactly does light see? What does the universe look like from the perspective of something that experiences no time? Can such a perspective even exist? Or are we approaching the limits of language itself? Because there is a subtle problem hidden here. The closer we move toward light's point of view, the stranger the concept becomes. Our thoughts depend upon time. Our perceptions depend upon time. Experiences require moments occurring one after another. Without time, what does it even mean to observe? What does it mean to see? The deeper we investigate, the more the question begins slipping through our fingers. And yet the mystery remains. A mystery hidden inside every ray of sunlight, every star, every galaxy, every photon crossing the universe at this very moment. In the next chapter, we will follow Einstein's reasoning further and discover why chasing a beam of light ultimately leads to one of the strangest conclusions ever reached by science. Because if time truly disappears for light, then the universe may look completely different from its perspective than it does from ours. Imagine that somehow, impossibly, you have built the fastest spacecraft in the history of the universe, not merely faster than a jet, not merely faster than a rocket, faster than anything humanity has ever created. You leave Earth behind. The atmosphere disappears. The planets become distant points. The sun shrinks into another star. And all the while, you continue accelerating. Faster, faster, closer and closer to the speed of light. At first, nothing feels unusual. The universe looks familiar. The stars remain stars. Space remains space. Time continues flowing normally. But as your speed increases, subtle changes begin to appear. Changes so strange that they seem impossible. The first thing to happen is not what most people expect. You do not notice anything unusual about yourself. Your heartbeat feels normal. Your thoughts feel normal. Your clock ticks normally. From your perspective, everything seems unchanged. This is one of the most important ideas in relativity. You never directly feel time slowing down. Time only appears strange when compared with someone else. Imagine two identical clocks. One remains on Earth. The other travels aboard your spacecraft. When the clocks are later compared, something remarkable happens. The traveling clock shows less elapsed time. Less time has passed. The effect is real, not an illusion, not a measurement error, a physical difference. Time itself has flowed differently. The faster you move, the larger the difference becomes. At ordinary speeds, the effect is tiny, almost undetectable. At 90% of the speed of light, it becomes significant. At 99%, it becomes dramatic. At 99.9%, reality begins behaving in ways that seem completely detached from everyday experience. Suppose you travel to a distant star. From Earth's perspective, the journey might require decades. Yet for you, only a few years pass, perhaps months, perhaps even less. The universe begins compressing itself around your motion. The faster you move, the stranger reality becomes. And this is not speculation. Particle accelerators observe these effects every day. Tiny particles, called muons, provide one of the clearest examples. Muons are unstable. At rest, they survive only a tiny fraction of a second before decaying. High in Earth's atmosphere, cosmic rays create enormous numbers of them. Given their short lifetimes, most should never reach the ground. There simply is not enough time. And yet they do. Millions of them. Every day. Why? Because they move near the speed of light. Their internal clocks run differently. Time slows down. The universe allows them to survive long enough to reach Earth's surface. Again and again, experiment confirms Einstein's predictions. The universe really works this way. Time is flexible. Not fixed, not universal, flexible. And once you accept this, a new question naturally emerges. What happens if you continue all the way? What happens if you actually reach the speed of light? At first glance, this seems like a perfectly reasonable question. Unfortunately, nature has other ideas. According to relativity, objects with mass cannot reach the speed of light. The closer you get, the harder further acceleration becomes. More energy is required, then more, then vastly more. The required energy rises without limit. An infinite amount of energy would be needed to push a massive object all the way to light speed. And infinite energy does not appear to exist. The universe enforces a speed limit, not because someone decided it should, because the structure of space and time demands it. Light occupies a unique position. It does not merely travel at the speed limit, it defines the speed limit. The speed of light is woven into the architecture of reality itself. It is less a speed and more a property of spacetime, a fundamental feature of existence. Yet even though massive objects cannot reach light speed, the equations allow us to approach it. Closer, closer, closer still. And as we approach, something extraordinary happens. Time slows toward zero. The distances shrink. The universe contracts in the direction of motion. Eventually, the mathematics points toward a remarkable conclusion. For something traveling at exactly the speed of light, no time passes at all. Imagine a photon born inside the core of a distant star, not a star nearby, a star billions of light years away. The photon begins its journey. It crosses interstellar space. It crosses intergalactic space. It travels through expanding cosmic structures. Galaxies form. Stars die. Planets emerge. Civilizations rise and fall. Billions of years pass. Eventually, the photon arrives. Perhaps it strikes a telescope. Perhaps it reaches your eye. Perhaps it is absorbed by a grain of dust drifting between stars. From our perspective, the journey required billions of years. But according to relativity, the photon's own clock records no passage of time, none. The moment of emission and the moment of absorption become adjacent. The journey disappears. The entire history of the universe between those events vanishes. And this is where our intuition begins to fail. Because what does it mean for no time to pass? Our minds are built from sequences. One thought follows another. One moment follows another. Experience itself seems impossible without duration. Yet light appears to inhabit a realm where duration no longer exists, a realm where the concepts of before and after lose meaning, a realm where the beginning and end of a journey become inseparable. This is one reason physicists often hesitate when discussing the perspective of light. Strictly speaking, a photon does not possess a valid reference frame in relativity. The mathematics breaks down before you reach that point. You can approach light speed. You cannot stand alongside a photon and ask what it sees. The question itself becomes problematic, and yet the equations continue pointing towards something profound. The closer we move toward light's domain, the less familiar reality becomes. Time fades away. Distance fades away. The ordinary structure of experience begins collapsing. And hidden within that collapse is a possibility that borders on the philosophical. Perhaps light does not experience a journey at all. Perhaps the photon's birth and death are connected in a way our everyday intuition cannot fully grasp. Perhaps what appears to us as a voyage across billions of years appears, in some deeper sense, as a single event, a single connection between 2 points in spacetime. This idea sounds almost mystical, yet it emerges directly from physics. No mysticism required, only mathematics, only relativity, only the strange geometry of the universe itself. The deeper we follow Einstein's reasoning, the more the familiar world begins to dissolve. Time becomes flexible. Distance becomes relative. Motion becomes intertwined with reality itself. And in the next chapter, we will explore the most astonishing consequence of all. Because if no time passes for light, then from light's point of view, the concepts of past and future may cease to exist entirely. And a universe without past or future is far stranger than most people have ever imagined. Take a moment and imagine the most distant object you can think of. Perhaps a galaxy billions of light years away. A galaxy so distant that its light began traveling toward Earth long before our planet looked the way it does today. Long before humans existed. Long before the dinosaurs. Long before Earth itself had finished forming. The numbers involved are almost impossible to grasp. Billions of years. Thousands of millions of years. Entire chapters of cosmic history unfolding, while a single beam of light crosses the darkness. And yet, if we continue following the strange implications of relativity, something astonishing begins to emerge, for light itself, those billions of years, may not exist. Not in the way we imagine. This is where the universe starts becoming truly difficult to visualize. Human beings experience reality as a sequence. One event happens, then another, then another. Time feels like a river carrying us forward. The past sits behind us. The future lies ahead. The present moves continuously between them. Everything about our experience depends upon this flow. Memory depends upon it. Thought depends upon it. Life itself depends upon it. Without time, nothing familiar seems possible. And yet relativity suggests that light occupies a very different relationship with time than we do. The closer an object moves to the speed of light, the slower time passes relative to outside observers. At 90% of light speed, time slows significantly. At 99%, it slows dramatically. At 99.999%, the effect becomes enormous. Push closer still, and the mathematics keeps moving toward the same conclusion. Time approaches zero, not almost zero, zero. And if no time passes, something remarkable happens. The distinction between past and future begins disappearing. After all, what separates past from future? Duration, the passage of moments, the existence of time itself. Remove time, and the familiar structure begins collapsing. Imagine opening a book and seeing every page simultaneously, not reading page 1 and then page 2, not progressing through the story, seeing the entire book at once. The beginning and ending coexist. The sequence vanishes. The distinction between earlier and later loses meaning. This analogy is imperfect, but it points towards something important. Our ordinary experience depends upon moving through time. Light appears to exist at the limit where that movement disappears. And because of that, some physicists describe light as occupying a timeless connection between events. Again, we must be careful. A photon does not possess a valid perspective in the same way a person does. Relativity does not allow us to sit inside a photon's reference frame, but the mathematics still hints at a profound reality. Consider a photon leaving the surface of a star. Eventually, it reaches a telescope on Earth. From our perspective, two events occur. Event 1, emission. Event 2, absorption. Between them lies a journey, a duration, a history. For light, the situation appears very different. The interval between those events collapses. The separation disappears. The universe seems to connect the 2 points directly. This is one reason some physicists describe photons as existing outside ordinary time. Not because they literally escape reality, not because they possess magical properties, because the structure of spacetime treats them differently. They move along paths where the usual rules begin breaking down. And once you start thinking this way, a fascinating realization emerges. Almost everything you see is ancient light. The room around you exists because photons bounce from surfaces into your eyes. The stars exist in your awareness because photons carry information across space. The sun exists in your awareness because photons travel from its surface to Earth. Your entire visual experience depends upon light. Every color, every shape, every face, every landscape, every sunrise, every sunset. Everything arrives through photons. Yet those photons may not experience the journey they enable us to perceive. The universe becomes visible through entities that do not appear to experience visibility themselves. Light reveals time while potentially existing beyond ordinary time. There is something deeply beautiful about that, and perhaps a little unsettling, because it suggests that one of the most familiar aspects of reality may also be one of the most mysterious. I often think of light as simple: a flashlight beam, a ray of sunlight, a star shining in the night sky. Yet beneath that familiarity lies a phenomenon that helped force humanity to rethink the nature of reality itself. Before Einstein, time seemed absolute. After Einstein, time became relative. Before Einstein, simultaneity seemed obvious. After Einstein, simultaneity became observer-dependent. Before Einstein, space and time appeared separate. After Einstein, they merged into a single structure called spacetime. And all of these revolutions began with one stubborn fact: the speed of light never changes, no matter who measures it, no matter how they move, no matter where they are. Light forced the universe to reveal its deeper geometry, a geometry far stranger than common sense ever imagined. And perhaps the strangest implication of all is that what we call now may not be universal. Imagine two distant events occurring in different parts of the galaxy. From one observer's perspective, event A happens first. From another observer's perspective, event B happens first. Neither observer is wrong. The order depends upon motion. The universe contains no single cosmic clock ticking for everyone simultaneously. Each observer carries their own version of time, their own slice of spacetime, their own reality. The implications are profound. The present moment feels universal. It feels shared. It feels objective. Yet relativity suggests something different. The universe may not possess one universal present. Instead, countless observers move through spacetime, each carrying their own perspective, their own experience of now. And at the center of all this sits light, the messenger, connecting different parts of the cosmos, the phenomenon that revealed the flexibility of time, the phenomenon that forced us to abandon our oldest assumptions, the phenomenon that may exist beyond the very thing it helped us understand. In the next chapter, we will follow this idea even further, because if time disappears for light, another consequence follows naturally. Distance may disappear as well, and a universe without distance is every bit as strange as a universe without time, perhaps even stranger, because the more closely we examine light, the more it begins to seem less like something traveling through the universe and more like something connecting the universe together. Imagine standing on a beach at night. Far out over the ocean, a lighthouse flashes. A beam of light leaves the lamp, crosses the darkness, and eventually reaches your eyes. The journey feels obvious. The light starts there. It ends here. Between those 2 points lies a distance, a real distance, a measurable distance. The light must travel through that space, or at least that is how it appears from our perspective. Yet if we continue following the implications of relativity, something extraordinary begins to happen. Not only does time shrink for light, distance shrinks as well. In fact, the two effects are deeply connected. This is one of the most beautiful aspects of Einstein's theory. Time and space are not separate things. They are woven together. Pull on one and the other changes too. The faster you move, the more dramatically this relationship reveals itself. Imagine once again that impossible spacecraft from the previous chapter. You accelerate closer and closer to the speed of light. 90%, 99%, 99.99%. As your speed increases, something strange happens to the universe in front of you. It begins to compress. Distances contract. The stars seem closer together. The gap between destinations begins shrinking. This effect is known as length contraction. And unlike many thought experiments in physics, it is not merely theoretical. It is a genuine consequence of relativity. The universe itself changes shape depending on motion. Suppose a distant star is 10 light years away from Earth. To someone standing on Earth, that distance remains 10 light years. But to a traveler moving near light speed, the distance appears much shorter. Perhaps only a few light years, perhaps less. The faster the traveler moves, the more dramatic the contraction becomes. Reality adjusts itself. Space bends to preserve the constant speed of light. And if you continue pushing this logic toward the ultimate limit, something astonishing emerges. At the speed of light, the distance along the direction of travel collapses completely. Just as time collapses, the journey loses duration. The path loses length. Again, we must be careful. A photon does not possess a conventional reference frame. The mathematics become singular at light speed. Yet the equations continue pointing toward the same remarkable idea. For light, the separation between origin and destination may effectively disappear. Think about what that means. A photon leaves the surface of a star. Millions of years later, it arrives at a telescope. From our perspective, it crossed an enormous gulf of space, a vast cosmic distance. But from the photon's side of the equations, both the time and distance shrink toward nothing. The beginning and end become directly connected, not separated by a journey, connected. This is one of the strangest consequences of modern physics. The universe that appears unimaginably large to us may not appear large at all, from light's relationship to spacetime. The enormous cosmic distances that dominate astronomy may effectively vanish. The gap between stars, the gap between galaxies, the gap between the beginning and end of a photon's life. All of it becomes something profoundly different, and suddenly, light starts looking less like a traveler. A traveler moves through space. A traveler experiences a journey. A traveler measures time passing. Light seems to do something else entirely. It appears to connect events. Imagine drawing two dots on a sheet of paper. One dot represents a distant star. The other represents your eye. To us, those dots are separated by immense distances and durations. To light, the separation may be far less meaningful. The two events become linked by a single path through space-time, a direct connection between emission and absorption. This idea becomes even more fascinating when we think about the age of the universe. Some of the light entering our telescopes today began its journey more than 13 billion years ago. The photons left distant galaxies shortly after the universe itself emerged from its earliest stages. They traveled across expanding space, across cosmic history, across almost the entire age of the observable universe. From our perspective, these photons are ancient travelers. They have spent billions of years crossing the cosmos. Yet, if relativity is taken seriously, the photons themselves do not experience those billions of years. The entire history of the journey collapses. The emission and detection become intimately connected. And this raises a question that sounds almost philosophical. If light does not experience time, and if light does not experience distance in the ordinary sense, what exactly is happening between its creation and destruction? What is a journey without time? What is travel without distance? What is motion without duration? The questions begin stretching language itself, because words like travel, movement, and journey assume the existence of time. They assume change. They assume progression. Light seems to occupy a realm where those assumptions begin breaking apart. This is one reason physicists often describe photons in ways that feel counterintuitive. The closer we examine them, the less they resemble tiny objects moving through space. Instead, they start looking like relationships between events, connections woven into the fabric of space-time itself. And perhaps that should not surprise us. After all, light has been quietly challenging our assumptions from the very beginning. It revealed that time is flexible. It revealed that space is flexible. It revealed that simultaneity is relative. Again and again, light has forced humanity to abandon comfortable intuitions. Perhaps its deepest lesson is still ahead, because there is another mystery hidden here, a mystery that becomes obvious once you ask a simple question. If light experiences neither time nor distance in the way we do, can it experience anything at all? Can a photon witness the universe? Can it observe stars, galaxies, or planets during its journey? Can light actually see anything? Or does the very concept of seeing require time, making the question itself impossible? In the next chapter, we will confront that mystery directly. Because when people ask what light sees, They are really asking something much deeper. They are asking whether experience itself can exist without time. And the answer may reveal why the universe looks the way it does to us, and why it may look like nothing at all to light. At first glance, the question seems almost childish. What does light see? It sounds like the kind of question a curious child might ask while staring at sunlight pouring through a window. Yet hidden inside that simple question is one of the deepest mysteries in modern physics, because seeing is not as simple as it appears. Most of us never think about what seeing actually means. You open your eyes, light enters, images appear. The process feels effortless, automatic, obvious. But beneath that apparent simplicity lies an extraordinary chain of events. Photons strike molecules in your retina. Chemical reactions begin. Electrical signals travel through nerves. Patterns emerge inside the brain. Memories are compared. Shapes are recognized. Meaning appears. What we call vision is not a single event. It is an entire process unfolding through time. And that final detail turns out to be crucial. Through time. Everything about perception depends on time. A thought requires time. A memory requires time. An observation requires time. Even the awareness of a single instant requires some passage of duration. Without time, experience itself begins to lose meaning. And this brings us back to light. Suppose a photon leaves a distant star. What happens during the journey? Our intuition immediately supplies an answer. The photon travels. It crosses space. It moves through the darkness. It passes planets and nebulae and galaxies. It witnesses the universe unfolding around it. The image feels natural, almost cinematic. A lonely particle crossing the cosmos while watching history unfold. But relativity suggests something very different. The closer we approach light's relationship with space-time, the less meaningful the concept of a journey becomes. No elapsed time, no experienced duration, no sequence of moments. And if there are no moments, what exactly could be observed? Observation requires change. Experience requires change. A witness requires change. Without time, there can be no before and after. Without before and after, there can be no experience. This leads to a strange conclusion. Light may not see anything at all. Not because the universe is invisible. Not because photons are blind. Because seeing requires a temporal framework that light does not seem to possess. The statement sounds simple. Its implications are profound. Think about the night sky. Every star you see is visible because photons reach your eyes. The entire visible universe arrives through light. Everything you know about the cosmos comes from photons. And yet those same photons may never experience the universe they reveal. In a sense, light acts as the messenger of reality without participating in the message itself. The courier does not read the letter. The bridge does not experience the travelers crossing it. Light connects events without necessarily experiencing the connection. There is something deeply beautiful about that, and perhaps a little tragic. The very thing that allows us to see the universe may never see the universe itself. Yet even that conclusion requires caution, because there is another possibility. A possibility that emerges when we stop imagining photons as tiny objects moving through space and start thinking about them the way modern physics does, as excitations of a field, as manifestations of the electromagnetic field, as quantum entities that do not fit neatly into ordinary categories. The deeper physicists investigate light, the harder it becomes to describe it using familiar concepts. Is a photon really a particle? Sometimes. Is it really a wave? Sometimes. The answer changes depending on the experiment. the answer changes depending on the question. This is one of the recurring themes of modern physics. Reality refuses to fit inside the boxes our intuition creates. Light behaves like a wave when spreading through space. It behaves like a particle when transferring energy. It behaves like neither when examined deeply enough. The closer we look, the more the categories begin dissolving. And nowhere is this more obvious than when we ask what light experiences. The question assumes light is the kind of thing that can have experiences. But perhaps that assumption is wrong from the beginning. Perhaps a photon is not an observer moving through the universe. Perhaps it is a connection between events, a relationship rather than a traveler, a process rather than an object. Imagine a bridge spanning a river. The bridge connects two shores, but asking what the bridge experiences during the crossing misses the point. The bridge is not a traveler. It is the connection itself. In some ways, light appears similar. It links events across spacetime. It carries information. It transfers energy. It creates causal relationships. Yet the closer we examine it, the less it resembles something undergoing a personal journey. This realization becomes even stranger when we consider the scale of the observable universe. Some photons reaching Earth today began their journeys shortly after the Big Bang. For over 13 billion years, they have crossed expanding cosmic space. They have traveled farther than any human mind can truly comprehend. From our perspective, their journeys are almost unimaginably long. But from the perspective suggested by relativity, the concept of a journey may barely apply. The emission and absorption remain directly linked. The separation collapses. The vast cosmic history between them becomes something profoundly different. And this raises a question that physicists rarely ask explicitly. Perhaps we have been thinking about light incorrectly all along. Perhaps light is not moving through space in the way a spaceship moves through space. Perhaps light is something more fundamental, something woven directly into the structure of space-time itself. After all, the speed of light is not merely a property of photons. This is one of the most misunderstood ideas in physics. Many people imagine that the speed of light belongs to light. But the speed of light is actually a property of spacetime. It appears throughout the equations of relativity. It governs causality. It defines the maximum speed at which information can travel. Even if photons did not exist, the same fundamental speed would still appear in the structure of reality. Light merely happens to travel at that speed. In some sense, light reveals the geometry of the universe. It acts like a guide to the deeper architecture beneath reality. And when we follow that guide, we begin discovering something extraordinary. The universe may be less about objects moving through space and more about relationships connecting events. Less about things, more about connections. Less about travelers, more about paths. The distinction seems subtle, yet it changes everything. Because if light is fundamentally a connection, rather than a traveler, then the question, what does light see, may not have an answer. Not because the answer is hidden, because the question itself belongs to a framework that no longer applies. And yet, strangely enough, exploring the question still teaches us something important. It teaches us about the limits of intuition, the limits of language, the limits of the concepts we inherited from everyday life. Light continues exposing those limits again and again. And in the next chapter, we will encounter perhaps the strangest consequence yet. Because if photons do not experience time and distance the way we do, then something astonishing follows. A photon may never truly travel at all, not in the sense we normally imagine. And if that is true, then every beam of light crossing the universe may be participating in something far more mysterious than a journey through space. Take a moment and think about what it means to travel, not in the scientific sense, in the ordinary sense. Imagine driving across a country, walking through a forest, flying across an ocean. Every journey contains the same basic ingredients: a beginning, a path, an ending, and most importantly, time. Travel is something that happens through time. You leave one place, moments pass, you arrive somewhere else. Without the passage of time, the concept itself begins to unravel. This seems obvious, almost too obvious to mention, yet it becomes surprisingly important when we return to light. Because everything we have discussed so far points toward a strange possibility. A possibility so strange that many physicists avoid describing it in simple language because it sounds almost mystical. And yet it emerges naturally from relativity. The possibility is this: light may never truly travel, at least not in the way we imagine. To understand why, imagine a photon leaving the surface of a distant star. Perhaps that star lies 1,000 light years away. From our perspective, the situation seems straightforward. The photon begins its journey. It crosses the darkness. 1,000 years later, it arrives. Simple. But notice something interesting. Everything about that description comes from our perspective, our clocks, our measurements, our experience of time. The photon itself does not appear to share that experience. As we have seen, relativity drives the passage of time toward zero for light. The closer we move toward light's domain, the less meaningful duration becomes. And if no time passes, what exactly is happening during the journey? Think carefully about that. If an event has a beginning and an end but no elapsed time in between, can we really call it travel? Or is something else happening? This is where our ordinary language begins to fail, because words like movement and travel assume a sequence of moments, a progression, a duration. Light seems to inhabit a limit where those concepts become increasingly difficult to apply. Imagine watching a movie. The story unfolds frame by frame. Characters move, events happen, time passes. Now imagine compressing every frame into a single instant. The entire film exists simultaneously. The distinction between beginning and ending vanishes. The story no longer unfolds. It simply exists. Again, the analogy is imperfect, but it hints at something important. For us, the universe unfolds through time. For light, the distinction between different moments may become profoundly altered. A photon emitted from a distant star and absorbed by your eye may be separated by millions of years from our perspective. Yet the structure of space-time seems to connect those events far more directly than intuition suggests. This idea becomes especially fascinating when we consider the observable universe. Every night, telescopes collect photons that have traveled unimaginable distances. Some began their journeys before Earth existed. Some left their sources before the Milky Way looked the way it does today. Some have crossed nearly the entire observable cosmos. To us, these photons are ancient travelers, cosmic messengers carrying information across billions of years. But from the deeper perspective suggested by relativity, the story becomes stranger. The photons do not appear to experience those billions of years. The universe experiences them. We experience them. The photons do not. And suddenly, the idea of travel begins looking increasingly human. Perhaps travel is something observers experience, not something photons experience. This realization leads to a subtle shift in perspective. We often imagine light moving through a static universe. Perhaps it is more accurate to imagine light defining the relationships that make the universe visible in the first place. After all, every observation depends upon light. Every image, every photograph, every telescope, every sunset, every star. Light is not merely another object inside reality. It is one of the mechanisms through which reality becomes observable. Without light, the cosmos would remain hidden. Distances would become unknowable. Structures would become invisible. History itself would become inaccessible. In a very real sense, light creates the observable universe. Not the physical universe, the observable universe. The difference matters, because everything you know about distant reality arrives through photons. When you look at the moon, you are seeing photons. When you look at the sun, you are seeing photons. When astronomers study galaxies billions of light years away, they are studying photons. Light is the messenger through which the cosmos reveals itself, and that messenger appears to occupy a very unusual relationship with spacetime. The more deeply physicists explore this relationship, the more extraordinary it becomes. There is a reason Einstein devoted so much attention to light. The path to relativity began with light. The path to modern spacetime began with light. Again and again, whenever physics approached a major breakthrough, light stood at the center. It was light that revealed the flexibility of time, light that revealed the flexibility of space, light that revealed the limitations of Newtonian intuition, and perhaps light continues revealing something even deeper, because hidden beneath all these discussions lies a remarkable fact. The speed of light is not simply fast, it is fundamental. There is nothing special about the number itself. 300,000 kilometers per second sounds impressive, but another universe could have chosen a different number. What matters is that this speed plays a unique role in reality. It defines causality. It determines how information spreads. It governs the structure of space-time. The universe appears built around it. And because of that, light begins to feel less like an object moving through space-time and more like a manifestation of space-time itself, almost like a feature of reality rather than a passenger within reality. This is one reason some physicists describe photons in unusually abstract ways, not as tiny bullets flying through space, not as little particles racing from place to place, but as excitations of the electromagnetic field, as relationships, as events, as pieces of a deeper geometric structure. The farther we move from everyday intuition, the more natural these descriptions become. And the farther we move from intuition, the more difficult it becomes to answer our original question. What does light see? Perhaps nothing, perhaps everything, perhaps neither concept applies, because seeing requires time. And the closer we move toward light's domain, the more time itself begins disappearing. Yet there remains one final mystery, a mystery even deeper than the disappearance of time. Because if light does not experience the universe the way we do, then perhaps our own experience of reality is more unusual than we realize. Perhaps the true mystery is not what light sees. Perhaps the true mystery is why creatures like us experience time at all, why we move from past to future, why moments unfold sequentially, why reality appears to flow. And in the next chapter, we will explore that question, because understanding light ultimately forces us to confront the nature of time itself. And the deeper we investigate time, the stranger our own existence begins to appear. Every moment of your life has been defined by a single experience, the feeling that time moves, not space, not matter, time. The sensation is so familiar that it almost disappears into the background of existence itself. You wake up. Morning becomes afternoon. Afternoon becomes evening. Days become years. Memories accumulate. The future becomes the present. The present becomes the past. Everything about being human seems tied to this steady flow. And because the experience is universal, most people assume it must reflect something fundamental about reality. Surely time flows because that is what time is. Surely the universe itself moves from past to future. Surely the future does not yet exist while the past has already happened. The assumptions feel obvious, natural, almost unavoidable. Yet when physicists began investigating the deeper structure of spacetime, something unexpected emerged. The equations did not contain a flowing present. They did not contain a moving now. They did not contain any special moment marching forward through the universe. Instead, they described something much stranger, a reality in which past, present, and future all coexist inside the larger structure of spacetime. To understand why this idea is so unsettling, imagine looking at a map. A map does not reveal a journey unfolding. The entire route exists simultaneously. The beginning of the road exists. The middle exists. The destination exists. The traveler experiences the route one section at a time. The map contains the whole thing. Some physicists believe space-time may resemble the map more than the journey. The universe, according to this view, does not continuously create the future. The future already exists as part of space-time. The past still exists as part of space-time. The present is simply the location you happen to occupy. This idea is often called the block universe, and while it sounds deeply philosophical, it emerges naturally from relativity. Remember what we learned earlier. Different observers moving relative to one another do not always agree about which events are happening now. The present is not universal. Two observers can disagree about the order of distant events. Neither observer is wrong. This fact creates a problem for the traditional picture of time. If there is one universal present, which observer gets to decide what it is? Relativity provides an uncomfortable answer. Nobody. There is no universal present. There is only space-time, and observers moving through it. The implication is difficult to absorb because it challenges one of the deepest intuitions humans possess, the feeling that the future does not yet exist, the feeling that the present moment is uniquely real, the feeling that time flows. Yet physics increasingly suggests that the flow may not belong to the universe. It may belong to us. This is where our story reconnects with light, because light occupies a unique position within space-time. It sits at the boundary, separating what can influence an event from what cannot. Every moment of your life is surrounded by an invisible structure called a light cone. The name sounds technical. The idea is surprisingly beautiful. Imagine a flash of light occurring right now. The light spreads outward in all directions. As time passes, the expanding sphere grows larger. If we draw this process on a space-time diagram, the sphere creates a cone-shaped structure. Everything inside the cone can be influenced by the flash. Everything outside cannot. The speed of light determines the shape of reality itself. It defines causality. It determines which events can affect one another. In a very real sense, light governs the architecture of experience. Without it, the universe would not possess the same structure of cause and effect. This is why physicists often describe light as something deeper than merely a phenomenon. Light is woven into the rules that make reality coherent. It helps define the difference between before and after, between possible and impossible, between connected and disconnected. And yet, paradoxically, light itself does not seem to experience these distinctions. The messenger defines the structure of time while standing outside many of its familiar features. The irony is extraordinary. The very thing that reveals the nature of time appears largely untouched by it. And this brings us to an even deeper question. Why does time seem to flow at all? If space-time already contains the future, why do we experience a moving present? Why do moments appear one after another? Why does existence feel sequential? The answer may lie not in physics alone, but in information. Consider a simple observation. You remember the past. You do not remember the future. That asymmetry shapes your entire experience of time. Memory points backward. Prediction points forward. The distinction feels fundamental. Yet the laws of physics are surprisingly indifferent. Most fundamental equations work equally well in both directions. Run them forward, run them backward. The mathematics often remains valid. This creates one of the greatest puzzles in science. If the laws are largely symmetric, why does time possess a direction? Why does the universe seem to move from past to future rather than the other way around? The leading answer involves entropy. Entropy is often described as disorder, though that description is incomplete. More accurately, entropy measures the number of possible arrangements a system can possess. Low entropy states are highly ordered and rare. High entropy states are common. The universe began in an extraordinarily low entropy state. Since then, entropy has generally increased. Stars burn fuel. Ice melts. Memories form. Structures evolve. The universe moves toward states that are statistically more probable. This increase in entropy creates what physicists call the arrow of time, the direction we experience as the future. And suddenly, something remarkable becomes visible. The flow of time may not be a fundamental feature of reality. It may emerge from the growth of entropy, from information, from memory, from the way conscious beings interact with the universe. The realization is profound. The passage of time that feels so immediate, so undeniable, so central to existence, may arise from deeper principles hidden beneath everyday experience. And if that is true, then light occupies an even stranger role than we imagined, because light exists at the boundary where many of our assumptions about time begin to fail. The closer we approach its domain, the more familiar concepts dissolve. Past and future blur. Distance contracts. Duration disappears. The ordinary universe begins revealing its deeper architecture. And in the next chapter, we will explore perhaps the most astonishing consequence of all. Because if light experiences neither time nor distance in the way we do, then every photon arriving in your eyes may be connecting you directly to distant events across the cosmos. Not through a journey, but through something far stranger, a relationship written into the geometry of space-time itself. At this very moment, photons are arriving at your eyes from every direction. Some bounced off the walls around you a fraction of a second ago. Some left the surface of the sun a little more than 8 minutes ago. Some began their journeys from distant stars years before they arrived. And some of the photons detected by the world's largest telescopes have traveled for billions of years. It is easy to think of these photons as messengers, tiny couriers carrying information across space. In many ways, that description is correct. But as we have discovered throughout this journey, the deeper we examine light, the stranger the idea of a journey becomes. Because from our perspective, photons travel. From the perspective suggested by relativity, something else may be happening, something far more profound. To understand why, imagine a distant galaxy, not one nearby, not one visible to the naked eye, a galaxy so far away that its light has spent most of cosmic history crossing the universe. Perhaps the photons leaving that galaxy began their journey 10 billion years ago. At the time, Earth did not look the way it does today. Human civilization did not exist. The continents occupied different positions. Entire species had not yet evolved. The universe itself was younger. The galaxy emitted light. The light crossed the expanding cosmos. Eventually, after 10 billion years, a telescope on Earth detected those photons. From our perspective, the story is clear. A beginning, a journey, an arrival, 10 billion years of travel. Yet the deeper implications of relativity continue pointing towards something radically different. The photon does not appear to experience those 10 billion years. The duration belongs to us. The history belongs to us. The photon simply connects two events: emission, absorption. The universe in between belongs to the observers, not necessarily to the light itself. This realization transforms the way we think about observation. Most people imagine that when they look into space, they are looking outward. And they are, but they are also looking backward. Every astronomical observation is an act of time travel, not science fiction time travel, real time travel. The moon appears as it was about 1 second ago. The sun appears as it was 8 minutes ago. The nearest star appears as it was more than 4 years ago. The Andromeda galaxy appears as it was over 2 million years ago. The farther you look, the further into the past you see. Astronomy is unique among sciences because its subject matter is history itself. Every photon carries a timestamp. Every beam of light is a fragment of the past arriving in the present. And because of that, the night sky is not a snapshot. It is a mosaic of different eras, different moments, different chapters of cosmic history. When you look upward, you are not seeing the universe as it is now. You are seeing countless versions of the universe from different times simultaneously. The realization is extraordinary. The stars overhead belong to different years, different centuries, different millennia, different ages of cosmic history. The sky is a collection of memories written in light, and yet those memories arrive through photons that may not experience time the way we do. Again and again, light reveals this strange duality. It creates our perception of time while standing at the edge of time itself. It reveals distance while existing at the limit where distance contracts away. It connects events while appearing not to experience the separation between them. The deeper we follow these ideas, the more light begins to resemble something fundamental, not merely a phenomenon, not merely a particle, not merely a wave, a connection, a thread woven through spacetime. This image becomes even more powerful when we consider the structure of the universe itself. Modern astronomy has revealed that galaxies are not randomly distributed. They form enormous structures, clusters, superclusters, filaments stretching across hundreds of millions of light years. Together, these structures form what scientists call the cosmic web, a vast network connecting galaxies throughout the observable universe. Seen from enough distance, the universe resembles a gigantic neural network, or perhaps a web of glowing threads suspended in darkness. The comparison is imperfect, but visually striking. And what allows us to see this web? Light. Always light. Every map of the cosmos, every image of a galaxy, every measurement of cosmic structure, every glimpse into the early universe, all of it arrives through photons. In a sense, light does more than reveal the universe. Light creates the universe we can know. Without photons, the cosmos would remain hidden behind an impenetrable curtain. Planets could exist, stars could exist, galaxies could exist, yet we would never see them. Light transforms existence into knowledge. And perhaps that is why it feels so fundamental. Not merely because it travels fast, not merely because relativity revolves around it, but because it acts as the bridge between reality and awareness. The universe becomes visible through light. The universe becomes understandable through light. The universe becomes part of human experience through light. There is something beautiful about that relationship. Every atom in your body was forged inside stars. Every atom around you participates in the same cosmic story. And the thing that allows you to witness that story is light, the same phenomenon that leaves distant galaxies, the same phenomenon that crossed billions of years of cosmic history, the same phenomenon that helped Einstein uncover the flexibility of spacetime, the same phenomenon that continues challenging our understanding today. And perhaps the most remarkable part is this: despite centuries of study, we still do not fully understand it. We know how to calculate light with extraordinary precision. We know how to manipulate it. We know how to build technologies around it: lasers, fiber optics, solar panels, telescopes. Entire civilizations depend upon our understanding of light. Yet the deeper philosophical questions remain. What is a photon, ultimately? What does it mean for something to exist without experiencing time? What does it mean to move through a universe where distance contracts away? What does it mean to be a connection rather than a traveler? The answers remain incomplete. And perhaps that is fitting, because light has always occupied a unique place in human thought. It reveals reality, yet it remains mysterious. It illuminates the universe, yet it conceals deeper questions beneath its glow. It appears familiar, yet becomes stranger the more closely we examine it. In the next chapter, we will bring these ideas together, because the question we started with, what does light see, ultimately leads somewhere unexpected, not toward an answer about photons, but toward an answer about us, about observers, about consciousness, about why the universe appears the way it does when experienced from within time rather than beyond it. And that final step may reveal that the deepest mystery was never light itself. The deepest mystery may be the beings asking the question. Throughout this journey, we have followed light to the very edge of our understanding. We have watched time slow down. We have watched distance contract. We have explored the strange possibility that a photon may not experience a journey at all. And now, after traveling so far into the nature of light, we arrive somewhere unexpected, back at ourselves, because hidden inside the question, what does light see, is another question, a deeper question, a question we rarely think to ask. Why do we see reality the way we do? After all, the universe does not come with labels attached. It does not arrive pre-organized into colors, shapes, sounds, and experiences. Those things emerge through observation, through interpretation, through consciousness. The world you experience is not reality directly. It is reality translated, translated by your senses, translated by your nervous system, translated by your brain. And nowhere is this translation more obvious than in light itself. Consider color. Most people naturally assume colors exist in the world. Red flowers, blue skies, green forests. The colors feel real. They feel external. They feel like properties of objects. Yet physics tells a different story. Outside your mind, there is no redness, no blueness, no greenness. There are only electromagnetic waves, different wavelengths, different frequencies. The flower is not red. The flower reflects certain wavelengths of light. Your brain transforms those wavelengths into the experience of red. The sky is not blue. The atmosphere scatters certain wavelengths more efficiently than others. Your brain transforms those wavelengths into blue. The colors exist, but they exist as experiences, not as independent features floating through the universe. This realization can feel unsettling, yet it reveals something important. The universe we experience is a collaboration between reality and observation, between photons and perception, between the external world and the conscious mind. And suddenly, our original question begins changing once again. Perhaps asking what light sees is the wrong approach, because seeing may not belong to light at all. Seeing belongs to observers. Light provides information. Observers transform information into experience. The distinction is profound. A photon can strike a detector. A photon can transfer energy. A photon can carry information across billions of light years. But seeing requires interpretation, meaning, awareness. The universe contains light everywhere. Conscious observers appear to be far rarer. And because of that, perhaps the greater mystery is not how light travels through reality. Perhaps the greater mystery is how reality becomes experience. Think about the photons entering your eyes right now. Some originated from nearby objects. Some may have bounced several times before reaching you. Every one of them carries information, patterns, structures, relationships. Yet the photons themselves do not experience those patterns. You do. Somewhere inside the activity of billions of neurons, information becomes awareness. The transformation is extraordinary. Physics can describe the photons. Biology can describe the neurons. Neuroscience can describe the signals. Yet the existence of subjective experience remains one of the deepest mysteries in all of science. Why should information feel like anything? Why should electrical activity become awareness? Why should a universe of particles and fields contain conscious observers capable of wondering about light in the first place? No one knows. And that uncertainty creates an interesting parallel. Just as we do not fully understand what light is, we do not fully understand what consciousness is. Both sit at the edge of scientific understanding. Both reveal extraordinary insights. Both remain mysterious. The photon and the observer, the messenger and the witness. Perhaps it is no coincidence that the two mysteries seem intertwined, because every observation requires both. A universe without light would be hidden. A universe without observers would be unseen. The reality we experience emerges from their interaction. And this brings us back to the stars. Every night, photons arrive from distant corners of the cosmos. Some began traveling before human civilization existed. Some began traveling before Earth possessed complex life. Some left their sources when the universe itself was young. The photons arrive. Your eyes collect them. Your brain interprets them. And suddenly a distant galaxy becomes part of conscious experience. A piece of the cosmos enters awareness. Think about how remarkable that really is. Atoms forged inside ancient stars eventually became living organisms. Those organisms evolved eyes. Those eyes collected photons from other stars. Those photons carried information across billions of years. And somehow, the universe became capable of looking at itself. Carl Sagan famously described humans as a way for the cosmos to know itself. The phrase has become famous because it captures something profound. The atoms in your body originated from cosmic processes. The light entering your eyes originated from cosmic processes. The laws governing both emerged from the same universe. Observer and observed belong to the same story. The separation is not as absolute as it first appears. You are not standing outside the cosmos looking in. You are a part of it. a temporary arrangement of matter contemplating the nature of light, a pattern within the universe attempting to understand the universe. And perhaps that is why the question, what does light see, resonates so deeply, because hidden within it is a reflection of our own curiosity. We want to know what light experiences because we want to understand reality from perspectives beyond our own. We want to step outside ourselves, outside time, outside ordinary intuition. We want to glimpse the universe from a new angle. Yet every attempt eventually leads us back to the same realization. The universe is stranger than we imagined, and we are stranger than we imagined too. In the final chapter, we will bring everything together. The nature of light, the nature of time, the nature of observation, and the remarkable possibility that the universe may be less a collection of objects moving through space, and more a vast network of relationships connected by light itself. As our journey comes to an end, it is worth returning to the question that started everything. What does light see? At first, it seemed like a simple question, a curious question, the kind of question that feels easy to answer. Surely light sees the universe. Surely a photon crossing space witnesses stars and galaxies passing by. Surely it experiences the enormous distances between cosmic objects. Yet the deeper we followed the science, the more the question transformed. The universe slowly removed one assumption after another. First, time began to disappear. Then distance began to disappear. Then the idea of a journey itself became uncertain, and eventually, even the concept of seeing started slipping away. By the end, we discovered something surprising. The question was never really about light. It was about reality. And perhaps even more than that, it was about perspective. For most of our lives, we experience the universe from a single viewpoint, the human viewpoint. We are creatures that live inside time. We remember the past. We imagine the future. We experience moments unfolding one after another. The flow feels so natural that we rarely stop to question it. Yet light occupies a very different position within the structure of spacetime. Not because it possesses magical properties, not because it escapes the laws of physics, but because it sits precisely at the speed that defines those laws. The closer we move toward light's relationship with reality, the less familiar reality becomes. The ordinary assumptions begin breaking apart. The universe reveals its deeper architecture. And that architecture looks very different from the world our intuition evolved to understand. Imagine looking at a tapestry from only a few centimeters away. You see individual threads, tiny details, local patterns. The larger image remains invisible. Now step back. The threads become part of something greater. A larger structure emerges. Relationships appear. Connections appear. Meaning appears. Perhaps our experience of time is similar. From inside time, life feels sequential. Moment follows moment. Cause follows effect. Past becomes future. But from a deeper perspective, space-time may resemble the completed tapestry, a vast structure containing relationships we can only glimpse from within. And woven throughout that structure is light, not merely as illumination, not merely as radiation, but as connection. Every photon links events, a star and an eye, a galaxy and a telescope, the past and the present. Light forms bridges across space-time. Without those bridges, the universe would remain fragmented, hidden, unknown. In many ways, light is what makes the cosmos a connected whole. This becomes especially striking when we consider the scale of existence. The observable universe contains hundreds of billions of galaxies. Each galaxy contains billions or even trillions of stars. The distances between them are almost impossible to comprehend. And yet, despite those vast separations, light links everything together. Information flows, relationships form, structures become visible, the cosmos becomes knowable. Imagine a universe without light, not darkness, a universe literally without light. No photons, no electromagnetic radiation, no way for information to travel across cosmic distances. The stars could still exist. The galaxies could still exist. The planets could still exist. But the universe would become isolated, disconnected, silent. Light transforms separation into connection, and perhaps that is why it occupies such a special place in physics. Again and again, whenever scientists uncover deeper truths about reality, light appears at the center of the story. It revealed relativity. It revealed quantum mechanics. It revealed the age of the universe. It revealed the existence of distant galaxies. It revealed the expansion of spacetime. Light has guided humanity through every major revolution in our understanding of the cosmos, and still, it remains mysterious. Even today, physicists continue debating questions that would have sounded impossible a century ago. What is the true nature of a photon? Why does quantum mechanics behave the way it does? How does space-time emerge? What lies beneath the quantum fields? What is the relationship between information and reality? The deeper we explore, the more questions appear, and perhaps that is exactly what should happen. Because the universe is not a puzzle designed to be completed. It is a landscape to be explored. Every discovery reveals another horizon. Every answer reveals another question. Every mystery opens the door to a deeper mystery. Light has been teaching us that lesson for generations. A simple beam of sunlight appears ordinary, yet hidden within it are clues about space-time, about quantum mechanics, about causality, about the origins of the cosmos itself. The familiar often conceals the extraordinary, and nowhere is that more true than with light. The photons arriving from distant stars tonight are carrying more than energy. They are carrying history, carrying information, carrying evidence about a universe larger and older than any human being can fully imagine. Some began their journeys before Earth was born. Some left their sources before our galaxy looked the way it does today. And now, they arrive here, at this moment, connecting distant corners of reality through a phenomenon we still do not completely understand. There is something deeply humbling about that. The universe is vast, ancient, complex beyond comprehension, and yet a small collection of atoms on a tiny planet can ask questions about it, can wonder about it, can study the nature of light itself. Perhaps that is the most remarkable fact of all. Not that light behaves strangely, not that time bends, not that distance contracts, but that the universe contains observers capable of discovering these things. Observers capable of questioning their own assumptions. Observers capable of realizing that reality is stranger than it first appears. And so, as the night grows quiet and your thoughts begin to drift, allow yourself to hold on to that sense of wonder. A photon leaves a distant star. A galaxy shines across the darkness. Light crosses the cosmos. And somewhere, on a small world orbiting an ordinary star, conscious beings look upward and ask questions. Questions about time. Questions about reality. Questions about light. Questions that may never be answered completely. And perhaps that is part of their beauty. Because some mysteries are valuable, not because they end, but because they continue leading us deeper into the universe. Thank you for joining this journey through the nature of light, time, and reality. And if you enjoyed this exploration, Consider subscribing and returning for another calm voyage into the deepest questions of physics and the cosmos. Until next time, sleep well.